Work fluently between multiple representations of exponential functions. And I'm very sorry if I start talking fast. It's just that, again, this is the fourth time I'm recording this. Um, Distinguish exponential growth or decay from other types. The general form of this is going to be, this is your parent function all of the time, and you'll see this throughout this entire objective, is y is equal to a times b to the x power. A is going to be your starting point, and B is going to be your rate at which it is moving, whether it's growing or decaying. So here we have, again, our parent function or your general form. And an example, we have y is equal to 2 to the x power. X is going to be any of the x values that you choose to plug in. Here I have 0 through 5. And when we plug our x values in, we will find our y values. As you can see, I had made a mistake. So when x is 0, y is actually 1. I don't remember what I had there before, but y should be 1. And it goes 2, 4, 8, 16, and 32. This pattern is being multiplied. And you'll notice that when you're trying to figure out what the pattern is, please try to do at least 3 or 4 times to make sure that it is going by the same rate every single time. So this one does go by 2 every time. So this potential growth means that it's increasing by multiplication or increasing by 2. Okay, we still have our general form, and we're using key features to represent and solve problems involving growth or decay. So here we have 50 bacterial cells that double every hour. Again, you're going to have to channel in and use those words that have meanings and figure out what they're meaning. So a double, it means that it's doubling. So by 2 every hour. How many cells after 4 hours? So we have our parent function where y is equal to the number of cells after time. X is equal to your time. B is your rate, which is 2 because it's doubling. And A is your initial value, which is 50. Okay, so we have A, we have B, we have X, and Y is going to be the number of cells. So we make our equation where A is 50, B is 2 to the X power. Here it's asking for 4 hours. So we plug in 4, 2 to the 4th power is 16. 16 times 50 is 800 cells. So if I were going to check this, I would probably make a table and start with 0 time. We know is going to be 50 cells because that's what we're starting with. And then we have 1 hour, 2 hours, 3 to 4. 100 cells, 200 cells, 400, and then 800. The question here is asking, which is an extended question, how many are there going to be after 2.5 hours? I can't really look at my table and see exactly how many are going to be after 2.5 hours. One, mainly because we are multiplying our rate by itself, which is our power. Okay, so instead of 4 hours, we're going to be plugging in 2.5 there. So we have 50 times 2 to the 2.5 power. And when we multiply that out, we get 282.8 cells. Okay, so you already have your equation. You just need to plug in the hours. So you're going to use key features, again, of this exponential function to represent and solve the problem involving growth or decay. So we need to figure out, is it growing or is it decaying? So this example is showing 30% of the plants die every year. There are 50 acres of plants. How many plants are left after 5 years? So again, with our parent function, we have y is equal to a times b to the x power. Y is the amount that's left. T is our time. X is our time. B is the rate. So we're going to look at, we have 30% here. And because they're dying, the plants are dying, that means it's decaying. So we need to use, we start with our whole number, which is 1, and we're subtracting the percent. So we have 30% over here. We need to change that to a decimal. So you're moving your decimal 2 places to the left. So you have 0.3 over here. 1 minus 0.3 is going to give us 0.7. That's left of our percent. So that's your rate at which they're dying every year. And A is going to be your initial value, which is your 50 acres. So again, just put in your variables just to make it a little bit easier for you to plug in to the equation. X over here is your 5 years. So I have already given you this equation. So we have y is equal to 50 times 0.7 to the 5th power for 5 years. And we get that after 5 years, there will be 8.4035 acres that are left. The extended question here is how much after a decade? Again, how much or how long is a decade? We know that is 10 years. You already have your equation that you created. So that's 50 times 0.7 to the 10th power. And we get that it is 1.4 acres left. All right. Write and interpret the exponential functions that describe a relationship between two quantities. We have our parent function here. And then we have, as you notice, there are more x values here. So I kind of plug more negative values in just so we can see a little bit more of the graph. And if you remember your exponential rules, when you have a negative exponent like we do here, 2 to the negative 4th, we need to, that goes under 1. So 1 over 2 to the 4th. Doing it this way gives us a positive exponent. So 2 to the 4th power is 1 over 16. So then we have 2 to the negative 3, and that is 1 over 2 to the 3rd. And that gives us 1 over 8, or 1/8. Okay, so that's just a little refresher, very quick refresher of negative exponents. And we plug in, so again, we're creating coordinates here. So we just plug those into the equation. And you can see that it creates this graph here. It looks like a little, almost like a little slide. And it's going up and down very close to the x-axis. So the question here that I have for you is, do you think it will ever get to 0? It's like, will the y value ever get to 0? The answer to that is no. It will get very close, but it will never reach 0. Okay. And then that's going to get into what that actually means. I'm going to skip the first exponential function definition right now, and I'm going to look at asymptote. Okay. Yes, it's a funny word. So what that really means is it's a line that a graph approaches more closely, but it's never actually going to touch. So here, when we said, will it ever get to 0? Because this line looks like it's approaching 0, it's never going to touch 0 because the asymptote is actually x is greater than 0. So it's never going to touch that. Here's the same thing. X is greater than 0. And that's what the asymptote is. It's approaching 0, but it's never going to reach it. Exponential function, you can see it has the parent function here. If a is greater than 0 and b is greater than 1, that is an exponential growth. Here we have our equation, which is, you can see is very similar. So we have our parent function 3 to the x right over here, but now we're adding in this 1/3. It's being multiplied. So we have all of our original numbers, 1/3, 1, 3, and 9. And now we're going to be multiplying it by 1/3. That is your factor, okay? So it's being multiplied by 1/3, and now we have our new y values, which are 1/9, 1/3, 1, and 3. So this, you can see the numbers are actually getting smaller from the first problem that we did, the first example. So 1/9 is smaller than 1/3, 1/3 is smaller than 1, and so on. So because the factor is less than 1, that means we have a vertical shrink. So this graph is actually shrinking by a factor of 1/3. Okay, our next example, you'll notice that we have 3/2 to the x power. However, we have this negative here. And what that means, that the negative means it flips over the x-axis. So we have our equation, or it's very similar to our parent function. We're plugging in our x values, and we're finding the answers to that. And once we do, we see that the graph is actually flipped over. Okay, now we're getting into some more things that look like translations, which you've probably, I'm not sure if all of you have taken that focus area yet, but if you did, you'll notice that like the translations were shapes that you were translating on the graph. So here we're actually doing translations with looking at pieces of the equation. So we have this parent function here, which is y is equal to a b to the x. So again, that is your parent function. And then you'll notice that it's added to the x power. We are still in the power form, but we're subtracting h, and then it drops to plus k. So you're beginning with the parent function, which is y is equal to a to the bx over here. And then you're going to switch it over to a horizontal translation. Remember, horizontal means you're going right to left, which is your x coordinates. So the minus h means you're moving to the right. If it was plus h, you would move to the left. Then you have a vertical translation. Vertical means up and down. The parent function means plus k, so that means you're going up. If it was minus k, that would mean you're going down. So let's look at this equation. We have 2 times 4 to the x plus 2 plus 1. All right, so we're starting with our parent function, which is 4. We're going to actually start with 4 to the x power. And we're going to plug in all of our x values in black over here to find what that is. 4 to the negative 1 is 1/4, right? So I'm going to highlight that in black over here. 4 to the 0 is 1. 4 to the 1, or the first power, is 4. 4 to the second power is 16. Then we go to this vertical stretch by a factor of 4. Because it is greater than 1, that means it is stretching. It's not shrinking, it's stretching. So we're multiplying now everything, and that means stretching means you're going up. Vertical means you're going up or down. So that we are looking at the y values there, or the y column. So you're going to now take your answers and multiply them by 2. 1/4 times 2 is 1/2. 1 times 2 is 2. 4 times 2 is 8. 16 times 2 is 32. We're done with that one. Now we're switching to the horizontal, your X numbers, a shift of 2 units. But however, in this example, it's saying plus 2, right? Here it was minus H. This is plus H. So I'm going to look over here. Plus means I move left. So I'm looking at my X values. And if I move 2 units to the left of -1, that means I get a -3. 2 units to the left of 0 is a -2. 2 units to the left of 1 is -1. And 2 to the units to the left of 2 is 0. Number 2 is done. I look at my last bit of equation, which is your plus k, and you'll notice here that it is in fact a plus. So perfect. I know I'm going up. This is not changing for me. Here we go. So plus 1. So that means we're going up. Going up means you're on the y-axis. So I'm looking at my y values. So 1/2 plus 1 gives me 3/2. 2 plus 1 is 3. 8 plus 1 is 9. 32 plus 1 is 33. So these points that I just circled are going to be the ones that you actually graph on the graph. Your domain, your X values are going to be all real numbers. Your range, which is your Y values, are all numbers that are greater than 1. I know it says 0 plus 1. That's because we would have start here. However, our asymptote is at Y is greater than 1. So that means your range is going to be greater than 1. Your asymptote is greater than 1. All right, so let's look at some problems that we're talking about growth and decay or increase with rates. We have this parent function here, y is equal to a times 1 plus r to the t power. A is your initial amount, r is your interest rate, meaning 1 plus r, and that's your growth factor. If it's 1 minus r, it's a decaying factor or decrease factor. T is your time in years. So we have this, it's kind of like a word problem, but you have $5 that you're starting with. That's your initial amount. You earn, which is a growth, 1% on your $5. Okay. So to figure out your rate, you're doing 1 plus, turning this percent into a decimal, 0.01. So your interest rate is going to be 1.01, which we have right here. Okay. So that's your equation, 5 times your interest rate to the t power. So if they were to ask you how much did you earn in 10 years, you plug 10 into your t to find your amount. All right, next problem is in 1970, the population was approximately, right, the squiggly line right here means approximately 333,000. From 1970 to 2000, it grew. So that means it's a growth problem, 2.4%. Write an exponential growth model. You're just writing the equation where P is the population, T is years after 1970. So what we have here is we have P is equal to 333,000. We're multiplying that by, it is a growth, right? So it grew. 1 plus, we write 2.4% as a decimal, so that's 0.024 to the t power. We would just clean this up a little bit, and we get 1.024 as our interest rate, and this would be your equation that you're working with. Okay, so now it's asking about how many people are sorry, I need to change this. How many people are going to be in 1990? So what I need to do is I need to look at how many years are between 1970 and 1990. So that means your t is going to equal 20. So I use the equation that I just created, and I do 333,000 times 1.024 to the 20th power. When we plug that into our calculators, and I encourage you to use calculators, you're going to get 535,110 people. Now we're looking into some compound interest. Okay, your apparent function for compound interest is A is equal to P times 1 plus your initial rate over your compound in time per year. And you're raising that to the power of your compound multiplied by your years. Okay, so here's what we do. We're going to look at this problem. There is a 3.6% annual interest. So that 3.6% is your R, right? You deposit $4,400. That's your amount invested. You're investing that much into your account. What's your balance after 2 years if the interest is compounded? So 2 years, that's your T that you're looking at. Okay, so we just kind of narrowed down the variables in this problem. And then we're going to look at the 2 points at which we're compounding. First, it's semi-annually. That means it's 2 times a year. So your N is going to equal 2 because it's semi-annually. So what I'm going to do now is I'm going to take all of the variables that I just figured out, and I'm going to plug them into the equation. So P is going to equal 4,400. And then we multiply that by 1 plus your rate. So we change that into a decimal, which is 0.036, divided by your compound, which here N is equal to 2. We raise that to the compound of 2 multiplied by the years, which is, again, 2. What I would do first is do everything that's inside the parentheses. Okay, do that first. When you get that answer, you're going to raise that to the power of whatever this is multiplied. So you're going to raise that to the power of 4. Then you're going to multiply all of that by 4,400, and you're going to get an answer of $5,906.82. If we were to talk about monthly, it's being compounded monthly, that means it's 12 times a year. So you are now taking your N, and instead of writing 2, you're going to change that to 12. All right, so again, you do everything on the inside, raise that to the power. Now this is going to be a power of 24. And then you're going to multiply that by 4,400. That gives us a value of $4,727.97. No worries, we will do many examples. Okay. Here we have a parent function of 1/3 to the x power. You can keep it as this and simply just plug it into your calculator to find the answers, or you can change this to 3 to the negative x power. We plug in our x values wherever we see x, and so we can find our y values and plot that on the graph. Okay, so this is an exponential decay because the fraction is less than 1. Here, this parent function is the same as the one above, right? So just like the last problem. However, we're multiplying it by 2. So this gives it a vertical stretch by a factor of 2. So it's being stretched upwards. So our new y values are going to be this. We're taking the values from above and we're going to now multiply them by 2. So we get 6, 2, 2/3, and 2/9. Okay, and so we plot those and we see just by looking at the two graphs that there is a vertical stretch there. Okay, so now we have a fraction that's less than 1. Again, so there's a decay, and we have this parent function of 3/4, and we're going to plug our x values into the parent function. Once we do that, we are going to then multiply by -2. Okay, so you can see we have that here. So we have -8/3, we have -2. This gives us -3/2 when it's simplified, and then -9/8 when it's simplified. All right, so now we're seeing that this does, remember the negative, it flips over the x-axis, so it flips it upside down. Okay, so now we have, again, one of those examples where we have some translations, and we're going to go right through it. So we're going to start with your parent function of 1/3. Oh, and I see a mistake here where this x to the x minus 2, that should be raised to a power of x minus 2. Okay, again, another reason why we definitely need to watch the videos so I catch my mistakes. So we start with our parent function, which is 1/3 to the x power, and we're plugging those x values in to get the answers of 3, 1, 1/3, and 1/9. Next, so that was done. You start with the parent function. Next, you're going to multiply your y by the 2. Okay, so we're taking the 2, your answers, multiplying by 2. So your new y values, which we will not plot yet, are 6, 2, 2/3, and 2/9. Okay, so that part is done. Next, we're going to look at your h. And we have -2, so that means we're moving 2 to the right on the x. So I'm going to have new values here. 2 to the right of -1 is going to be 1. And we have 2, 3, and 4. So those are now our new x values. And our final step is our +1, which is you add 1, so you're shifting up on the y. So I go back to my y and I'm adding 1. So my final y values are going to be 7, 3, 1 2/3, and 1 2/9. So I'm going to plot these numbers in the red circles into my graph, and this is what we get right over here. All right, so your asymptote is at y is greater than 1, because it is never going to approach 1. We have a decay here, a decay model. So we are given this example. A new car cost $25,000. The value of the car decreases by 15% each year. So we have this parent model here again, except we don't add your interest rate, we're subtracting it. So you're going to write an exponential decay model. That means you're writing the equation, giving the car's value y in dollars after so many years. So what I'm going to do first is figure out what the rate is. I write my percent in decimal, and I subtract it from 1. So that's 1 minus 0.15, which gives us 0.85. That's what we've done here. So our equation is 25,000 times 0.85 to the t power. That's it for that. Next, it's asking, estimate the value after 4 years. So what is the value of the car going to be after 4 years? We just plug 4 into where you see t, And then you'll find when you solve that, you get $13,050. Okay. This we are not going to do because that is probably something you would do, if not next year, the year after. So we're not going to do that. Here's a few visuals and reminders of practice, what exponential growth looks like. If your Y column is increasing, okay, so the numbers are increasing as you go down or as the X values move up, you're seeing that it's being multiplied by 2 here. So that means it's an exponential growth. Here, the Y values are decreasing as the X values move up. And we're finding that it's actually decreasing by half. So that means there's an exponential decay. More on this again. We have our parent function. So when it's growing, we have this growth increase. That means the absolute value of the common ratio is greater than 1. Okay, so it's going from the left at below, and it's moving up in like a slide form to the right. It's going up to the right. Your growth decrease, when it's shrinking, the absolute value of the common ratio, another mistake, is greater than 1. And so I did do that here. Decrease. Nope. It should be greater than 1. Sorry. And we have, so the decrease is going up from the left and down to the right here. Sorry, I was just making sure I was saying that all correctly. All right, some practice problems. You're rewriting each percent as a decimal. We've gone over this. You're moving 2 to the left. Evaluate each expression when x is equal to 3. So you're given an expression. You just need to plug 3 into wherever you see x and solve. Classify each as exponential growth or decay. So you're given these examples, and we went over how to figure out if there's a growth or it's a decay. Remember, if it's less than 1, it's what? If it's greater than 1, what is it? You can also, on these examples here, look at what's going on in those parentheses to figure it out. You can just write a G or D for growth or decay. We have these word problems here where you can label each of the problems with your A, B, and T to help you figure out how to solve this. Remember keywords here for triple. Triple means what? So then we have population of 1,000 will double. And what does double mean? A little sneaky trick here, trying to trick you up. The first example, it's asking you to find for 24 hours. But then for part B, it's asking for 5 days. Remember, we're not looking for days, it's asking for hours. So what are you going to need to do to those 5 days? Okay, you need to do some changing your days into hours. We have some growth and decay here. We have an increase by 15%. So you're going to be doing your 1 plus R. A baby weighs 7 pounds at birth with an increased weight of 11%. So again, we have a growth. You deposit money into an account and it's giving you interest. All right, so again, that is a growth, but it's being compounded annually. What does annually mean? And how much will be in the account after 8 years? All right, so remember this one is going to be compound equations that you're using. Radioactive material decays at 10% a year. All right, so we finally found a decay one where it's decaying, so that's 1 minus R. And then find the value of a downtown office building that cost $12 million to build 20 years ago. And it depreciates. So the word depreciate means it's decaying. So 1 minus R again. All right, we're up to check for understanding. Here, you're given your X values. I gave you X values here. and you just need to plug them into your equation and then write your answer down here on the right side of the column. This is for the next one. You have a different problem. Again, you're given your x values, plug it into the equation, put the answers in the column. When you are done, click turn in the Google class when you're done so I can check this and see if you're ready to take the focus area. And then we can go over, if not, things that you are struggling with. Okay. If you have any questions, please reach out. You know that you can always message me on Remind if you have any questions, and I'll get back to you with how to solve those problems. All right. Have a good one, guys.